brief, just name and from which institute? Please get seated and tell. No need
from Indian Institute.
Sir, Jagmohan Morana, Einstein Guru. Sangram Fishery sir, Rajdhani
सुशांत को आप लोग सर थोड़ा सा
Kumar sir, East Institute of Engineering and
So all of you are teaching electrical machine too?
Yes sir. Yes sir.
Because you are already teaching experience in electrical machine too. This just refreshing. Refreshing. I am not going to tell anything new. You are already teaching something. Still, whatever it will be more fruitful if you ask your point and we discuss on that. Good point. You could discuss that will go. Still, as my part of duty, I will go through that. But in between, wherever you want to discuss something deeper, part we will discuss. Okay. The syllabus, everything you know, POs you are know. Now whether PO 12, probably now it is PO 11. Now PO 11, it is to 11. That's 3 PSO. Okay. So these things you know already. COs 5 that is defined for the course, and these are course learning outcomes. You know for course wise learning outcome that is 5 according to your Bloom's taxonomy. You know all these things. Okay. These are the 30 reasons. And COPO mapping, and 3 strong, 2 moderate, 1 weak. Those things you know. You set some target for each CO, how many, according to how do you assign 1 or 2 or 2. These are the textbooks that is university has established. So we start from 3-phase induction motor. So the 3-phase induction motor is the main workhorse of the industry. It is told workhorse because after steam engine came, industrial revolution, industrial revolution, horse was before that horse is used for all the activities. So horsepower. So it gives the main strength. So induction motor now is for all industrial drives, induction motors are the best size. So it is the main workhorse of the industry. Okay, so trucks and all those things if you want you can discuss. So like there is a rotor and stator. Stator is cylindrical structure with a bore on it. Inside the bore, rotor is carried by the bearings, shaft and bearings. And then stator carries a 3-phase winding. Stator has slots on it, and it carries distributed winding. 3-phase distributed winding of the 3-phase induction motor. And rotor can have a 3-phase distributed winding on the slot like stator winding, or it can be simply like a parrot cage, squirrel cage or parrot cage like that. Accordingly, there are 2 types of induction motor. One is squirrel cage rotor induction motor, another is wound rotor induction motor. wound rotor means winding is there, rotor has a winding, it is 3-phase distributed winding, and the other one squirrel cage rotor, it is the rotor bar on the slots they carry, bars, conductor bar, and at the both ends of the so they are supported, the bars are supported by end rings, so that is called squirrel cage rotor induction. So the structure is there, these are the squirrel cage rotor and wound rotor induction motor. In wound rotor induction motor, because the rotor is carrying winding and it is to be, the terminals of the rotor has to be taken outside the rotating rotor. In the squirrel cage rotor, it is not required. There is no external connection from the squirrel cage rotor to outside. But in the slipping induction motor, rotor terminals have to be provided so that from external side, outside, we can access the rotor winding. So obviously slip rings will be there, and slip rings are rotating rings, and they make the contact. It is not like commutator and cross. In DC machine we have commutator and cross. Armature is rotating, so we take through commutator and cross. So there the commutator changes the frequency, but here only slip rings are there. Slip rings are rotating, and corrections are there from the winding to the slip ring, and then from slip ring they are connected to external terminal. So there is no frequency conversion, only external connection is taken out. So these photographs are showing that. Then main here is rotating magnetic field. So rotating magnetic field. What is the rotating magnetic field? Let us have a comparison with DC machine. In DC machine, we don't have rotating magnetic field. There in DC rotating magnetic field, the armature is on the rotor in DC machine, armature is on the rotor, and the stator carries the field poles and field winding. So their field is stationary, constant amplitude and steady field, not rotating field. And because armature is rotating, because of the relative speed between the stationary field and rotating conductor, in EMF is induced because of that. But in case of slip ring induction motor, rotor is separate. Rotor is different. First, stator. Armature in DC machine, armature means it is there on the rotor. In induction machine, when we say armature, we also can use the armature, but it is not rotating. It is stationary. It is the stator. So it is called stator. Stator means stationary armature. Basically, abbreviated stationary armature. It is the distributed winding. It is the main winding, armature winding, but it is stationary. Then it is the only supply source. Stator's only supply source comes to the machine through stator. Then stator is not moving, and there is no magnetic separate field winding. In induction motor, there is no separate field winding or field pole. Then how the field flux, which is essential for the electromagnetic energy conversion, say from in motor, it will be from electrical to mechanical. How that energy conversion can take? There is no field winding, no field pole. So there is a rotating magnetic field is produced. Why it is? How it is produced? So in this case, the figure is shown here, and you can show 3-phase distributed winding is out of the stator slot. These windings, 3-phase distributed windings, they carry 3-phase distributed current. 3-phase current RYB, the 3 phases, they are phase shifted by 150 degrees from each other. So when this 3-phase stator winding carries 3-phase distributed ballast current, a rotating magnetic field is produced. How that happens? You can draw it by drawing phasor diagrams. So I will take some time. You have taught it, so you are familiar. So I will show the concentrate my 3-phase windings like this. Board is visible to all.
Yes.
the three-phase distributed winding, say phase R, phase Y, phase B. The distributed winding of one phase I have shown as a concentrated coil, single coil. This winding, this is carrying current, R phase current, Y phase current, B phase current. Distributed current. Then this each winding will have a MMF. What is MMF? Magneto-motive force. That is equal to number of turns. Number of turns in this into current. Current now instead of now I will use instantaneous current N into IR for R phase. Similarly, for B phase, Y phase, they will also have MMF.
It is producing flux pi R, phi Y and phi B.
Three phase fluxes.
MMF by reluctance.
So flux is MMF by reluctance. That is fine. So at a particular moment, say at time t equal to t1, time particular fixed moment. Okay. So if current IR equal to the maximum current, let us say current IR equal to maximum current, then what will be IY and IB? Always all three current. So this is maximum means, so this is sin theta. So this is theta is 90 degree. This will be theta minus 120. So it will be minus Im by 2 and minus Im by 2. Okay. Alright. So if we draw the MMFs, say for this at time t1, this MMF is this is I am writing F for phase R. MMF for phase R, this is the maximum. This is along same axis, and along y axis, this MMF is Fy, and this MMF is I have shown one longer line. This is half of that because proportional to current. The MMF is proportional to instantaneous current, and their phase is this is the space position. Okay. So if you draw the resultant MMF at this moment, so what will be the resultant MMF at that particular time?
1.5
is 5. Right. You see, there is a vertical component. This vertical component of both the MMF will cancel. Vertical component will cancel. These two will cancel. Now horizontal component of FB and FY. This angle is 60 degree. This is FM by 2. If FR equal to I am writing FM. M means for maximum corresponding to magnetic maximum current IM. Then this is IM by 2. So its magnitude is FM by 2. Its magnitude is FM by 2. Okay. So this is 60 degree. So the component of FB in the horizontal axis is by cos 60 degree. Half of that cos 60 is 1 by 2. This is also 1 by 2. Okay. 1 by 2. So 1 by 2 into 1 by 2 total will be FM by 2. FM by 2. Okay. Then this is one thing. Then it will be its current is minus Im by 2 minus Im by 2. Okay. So its direction will be opposite. Instead of direction will be opposite like this. because current magnitude is minus Im by 2. So total component will be Fm plus 2 into Fm by 4. Fm by 4 because this is Fm by 2 minus Fm by 2. So and by 2 Fm by 4. So resultant is 3 by 2 into Fm. So at time t equal to 1, the MMF is total MMF is 3 by 2 Fm. Where what is Fm? That is number of turns into maximum current. So this is the resultant MMF at time t equal to 1. Its magnitude is 3 by 2 Fm into Im and direction is in this direction. Direction is in this direction. Okay. Then after some time, say you do again same thing. Its magnitude will be 3 by 2 Fm, but its position will be different. Because these windings are distributed windings. And the space position of the equivalent winding is like this, but current is sinusoidal and it is varying. So the axis of the current, at this point it is Im. After some time it will be, say, when omega t2 equal to say theta 2. This is corresponding to t1. Then after at time t2, the angle is, this is I am writing omega s into t2 is theta 2. Then this will be Im cos theta 2. Because current magnitude is varying with time. And this will be different. Resultant will be 0. So in this way, the direction of the resultant MMF, that is, this is the resultant MMF, its position is rotating. It is rotating MMF. So this MMF is rotating at the speed which is called the synchronous speed. So these figures are there. So you have understood, nothing to teach you because you are already teaching machine 2. Just I took my interest, out of my interest I explained. So it is nothing new to you. So this way resultant MMF is produced. MMF magnitude resultant is 3 by 2 into maximum MMF of one phase Fm, that is N into Im, and its resultant MMF has a direction. It is that the direction of the resultant MMF is constantly changing. So MMF is rotating, which at synchronous speed. And what is that synchronous speed? That is given. The magnitude of the speed is 120 into F by P. F is the frequency, P is the number of volts. So that way, synchronous speed is defined, and then this is one thing. So after the rotating magnetic field is produced, then this rotating magnetic field is rotating in the air gap, and the rotor conductor, whatever winding is there, distributed winding or concentric winding, whereas the slipping winding, squirrel cage rotor. The rotor conductors are stationary till now. The rotor conductors are stationary. Magnetic field is rotating. So because of the relative speed, EMF will be induced. So because winding is closed, current will be circulated, and that current, that rotor conductor current, it interrupts with the rotating flux in the air gap. And when you know by the principle, when a current carrying conductor is there in the magnetic field, it experiences a force. From the same principle, that force acting on two diametrically opposite conductors, it produces a torque. So that way torque is produced, and that torque does what? Torque makes the rotor to rotate. Why it rotates? Because again another law is there. Electrical engineers, all of you know Lenz's law. So Lenz's law, it defines, it tells electromagnetic induction will, wherever electromagnetic induction is there, I am not telling the statement, I am explaining. So the nature of the electromagnetic induction is such that it opposes the cause that produces it. Okay. The nature of the polarity. So what is the cause of the electromagnetic induction on the rotor? That is the relative speed. Relative speed. Because there is a rotating magnetic field and it is rotating with respect to the rotor. So because of the relative speed, the EMF is induced. And the EMF induced will be such that, and the current will be such that the resulting torque will minimize the relative speed. That is the cause is relative speed. So the induction will be such that the relative speed will reduce. So the rotor will rotate in the same direction as the magnetic field. So relative speed reduces. Relative speed means speed of the rotating magnetic field with respect to the rotor conductor. The relative speed reduces. So as the relative speed reduces, it will reduce to up to a point. After that, it will continue to rotate at that speed. Because suppose it rotates, the relative speed, the magnetic field is rotating at synchronous speed. Rotor was initial zero at stationary at zero. So initial relative speed was synchronous speed. Speed of the stator minus speed of the rotor is zero, synchronous speed. The speed reduces, but if the speed becomes zero, relative speed becomes zero. That means rotor is also rotating at the synchronous speed. Same as the stator. So relative speed will be zero. But then there will be no induction. Though the relative speed is zero, there will be no electrical induction. If there is no induction, there will be no torque. No torque is there, no induced torque is there due to induction. Then there are always frictional forces. Like air friction is there, air gap from air is there, air friction is there, bearing friction is there. So rotor shaft that is supported by the bearings. So bearing also friction is there. So these frictional forces will produce a torque which was opposing the rotor. So now that will not allow the rotor to rotate at synchronous speed. So the speed will be slightly less than the synchronous speed. Okay then. So this is the principle of operation basically I am explaining. So the rotor currents produce another magnetic field. Then again the stator magnetic field induction I have already explained. Now then rotor in the same way, rotor is carrying current and there will be some MMF. So rotor MMF is also produced and initially rotor is stationary. Initially before rotor rotation starts. Before rotation starts, rotor was stationary. Then stator is rotating, stator MMF is rotating at synchronous speed. So there will be induction in the rotor. What is the EMF? What is the nature of the EMF induced in the rotor? Nature of the, when you say it is alternating EMF. Alternating EMF has two things. One is its magnitude, RMS value, another is frequency. I am talking about the RMS value. Instantaneous value I am not talking because it is alternating quantity. It is like a sinusoidal. It has some RMS value. I am talking about the RMS value and the frequency. So before the rotor starts rotating, magnetic field is rotating at synchronous speed all the time. Rotor was altered. The relative speed was synchronous speed. Relative speed, that is synchronous speed because rotor is not rotating.
The sleep was one, sir. The sleep is one.
Sleep is one, yes. Magnetic field is this, rotor speed is zero. Rotor speed is zero. So sleep is one. All of you know what is sleep? Sleep is one. So induced EMF has the rotor induced EMF has the maximum value. Let us say it is some E0 I am right. It is the maximum value. Okay. And rotor its frequency FR
50 hertz, sir.
same thing. Stator supply frequency.
Same as status.
It's same as I am writing F1 means stator supply frequency. So stator supply frequency is also equal to rotor. Both are equal. Because rotor is stationary and relative speed is synchronous speed. That means 50 hertz. Supply voltage 50 hertz.
Sir, R is equal to S into Fs. So S is 1, so it is equal to Fs.
Fs.
Is
S
S.
into F. Yes.
So whenever the rotor is rotating with a slip S, then rotor frequency F are equal to S into supply frequency. Supply frequency 50 hertz. If the slip is at 10%, let us say 10%, then 50 hertz supply frequency. So what is the rotor frequency?
5%.
10%, 5 hertz. So rotor frequency is 50 hertz, 5 hertz. And what is the magnitude of the rotor induced RMS value of the rotor induced EMF?
Yes,
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 into
E0 is the EMF induced in the rotor RMS value when the rotor is not rotating. If the rotor is rotating at a slip S,
Yes,
S into E0.
Sleep
So
times.
if the slip is 10%, I told slip is 10%, that means 1/10 of the E0 will be produced at that condition. So it depends upon that. So this is what. So this rotor EMF, because this rotor induced EMF, whatever its magnitude, at any speed it is S into E0, and magnitude and frequency is SF, and then rotor carrying this current, and it will produce a magnetic field. Okay. Let us consider slip ring induction motor. Slip ring induction motor has a three-phase distributed winding. Slip ring induction motor. It is carrying a alternating current whose magnitude is S times E0 RMS value and frequency is S times the supply frequency. Now this will produce a rotating magnetic field in the same principle like stator was carrying three-phase current and produce the magnetic field. Rotor is also carrying a rotating magnetic field. What will be the speed of this rotor magnetic field with respect to rotor? Let us like stator core was not rotating, it is fixed. Because 50 hertz supply was given, it was produced at a speed ns equal to 120 A by P. Similar thing applies to the rotor. Now rotor frequency is FR
S into F.
into 120 into rotor frequency by P. Okay, this is what I'm writing what I want to tell ns. This is NR. FR is the rotor frequency of the rotor induced EMF. This is the NR. This is not rotor speed. This is what speed of the rotor EMF with respect to rotor. I am writing that. Speed of rotor EMF with respect to rotor. Now rotor is rotating at a speed.
Minus S into Ns.
I am writing FR is S times F1. So FR is S times F1 when the slip is there. So this is when FR equal to S times the supply frequency, then the speed will be NR will be S times NS. S times NS. Okay. Now this is with respect to rotor. Then with respect to stator, what is the speed? With respect to the absolute speed. Rotor speed is, let us rotor speed I am writing. You don't compute the rotor speed is omega. I am writing Nm. N mechanical speed of the rotor. N mechanical speed of the rotor. The relative speed this is S times Ns. The speed of the magnetic field with respect to the rotor is Sns. Now actual speed of the MMF with respect to you have to add. So this is again Ns. And so mechanical speed is it is 1 minus this is 1 minus S times Ns. mechanical speed, you define the slip such that the actual speed of the rotor is 1 minus s times the synchronous speed. And magnetic field with respect to rotor is rotating at a speed s and s. If you add them, actual speed of the rotor MMF with respect to the stator core is ns. So that means rotor magnetic field and stator magnetic field both are rotating at the same speed. Both are rotating at the same speed. Okay. Then the relative speed between them is 0. Thing is, they are not along the same axis. Another thing, the rotor MMF, how the rotor MMF is produced? Rotor MMF is produced because of the electromagnetic induction. And by Lenz's law, it will rotate at the same speed with respect to the stator MMF, same speed with respect to stator MMF. And thing is, they don't exactly cancel each other because some current is drawn by the stator to produce the magnetic field. Okay. So if you draw the, let us say, I will come to the phasor diagram, but remember, suppose this is the flux, I am just going quickly, so this is the core flux in the air gap core. Then the EMF induced in the rotor is 90 degree behind the flux. This is the EMF, induced EMF. Okay. So it carries a current I2. Rotor current carried by the rotor is lagging by angle phi 2. Rotor impedance angle. Rotor has resistance phi. And this current I2, when referred to stator, is I2 dash or minus I2 dash, whatever you write. I2 dash or minus I2 dash. Then this core flux is produced by magnetizing current IM because the current is required to produce. Then there is a loss component of the current. Some core loss will be there. This is the loss component of the current. So this is the no load current. So I0 is the no load current. Even if there is no shaft load on the load on the shaft, still stator will draw some current. That current does two parts. One is producing the flux phi m by the component IM, then providing for the core losses, that is IM. This total current is I0. When the load is provided, the rotor carries extra current, I2 dash. Then with respect to the stator, this is I2 dash, and resultant of these two currents is current drawn by the stator. Alright. This way, the torque is produced as a result of interaction of these two magnetic fields, stator MMF and rotor MMF, and the induced torque. And this is the torque. Induced torque means electromagnetic torque. We tell electromagnetic torque because torque is produced by electromagnetic interaction. So that part something I am discussing. I am not going as per the slide because you have already taught. There is no the slides also we will get, so you can use for your classes. So can the induction motor run at synchronous speed? Why? That you know, and we have also discussed. Nothing new. Because of the air friction and bearing friction, some frictional torque is there which opposes the rotation. So at synchronous speed, torque developed is induced is 0, so it will rotate at a speed less than that. Then speed falls and caught the rotor windings and the torque is produced. Then these things are only three, you know, slip speed is equal to synchronous speed minus mechanical speed of the shaft. The slip speed. And this is the slip defined by this. Slip is synchronous speed minus mechanical speed of the rotor by synchronous. If the rotor is stationary, slip is 1 because mechanical speed is 0. So numerator and denominator both at synchronous speed, so slip is 1. If the rotor runs at synchronous speed, Then Nm mechanical speed Nm equal to synchronous, so numerator is 0, so slip is 0. So slip may be expressed as a percentage. So like 10% or like that we can. Induction motors and transformers.
Sir, if the slip is negative, then it will go into the generating mode.
High.
Induction generator.
Induction generator.
That is possible. Thing is, we know that in a motor, the input is electrical power and motor converts it to mechanical power, and we get it at the start. In case of the generator, it is mechanical energy to electrical energy conversion. Generator takes mechanical power input and gives electrical power output. So like DC generator also, induction machine can operate as induction motor can operate as induction generator both. So input has to be given to the shaft. If mechanical power input is given at the shaft in form of torque, which shows that it drives the rotor at a speed higher than the synchronous speed, then it will act as a generator. Because mechanical speed of the rotor is now more than the synchronous speed, slip is negative, and it will act as generator, and in this case, rotor magnetic field is rotating at a speed higher. No.
Negative.
Slip is negative, so relative speed is opposite direction. Relative speed direction reverses because rotor is rotating at a higher speed. So induced EMF current change direction.
Sir, in another method, voltage can be also induced in the armature so that will take the speed beyond synchronous speed.
That is fine.
Give it a super synchronous speed.
That is also. So these techniques are used in the induction generator. There is a lot of wind turbines. We are using wind turbines. So many wind turbines use induction generator. So in induction generator, wind turbine drives and power is produced. If slip ring induction motor is there, slip ring induction machine, then from rotor side also we can control to get power at the output at the stator. So these are simple things which we have discussed everything. These things you know, you understand, anything new here? That you know. N is the slip speed and the Fr is the rotor frequency in hertz. What would be the frequency of the rotor at any speed? So that we have discussed. Sf is the frequency and magnitude of the EMF is h times the frequency at standstill condition. So sometimes to determine the parameter we do block rotor test. We use this block one here, block rotor test, no load test. If the motor is a machine is a no load, its speed is not synchronous, speed is slightly less than the synchronous speed, but it is the maximum. That is called no load part. But another, if the machine is totally blocked, you don't allow. Means rotor, you put a handle, you cannot by hand you cannot stop it from rotating. So we put a handle and that will not allow it to rotate. So in that case, rotor is not rotating, stator magnetic field is rotating at full speed, synchronous speed. So the EMF induced will be magnitude of the induced EMF and is maximum because the EMF is always slip times the. So slip is 1, rotor is not rotating with block condition, the slip is 1. So magnitude of the induced EMF is maximum, frequency is maximum, current is maximum, torque is also maximum. But that you require high torque to block the rotor from rotating. So that is not block rotor condition.
Sir, company जो mechanical speed और rotor speed इटा कौन समान ना
No.
I understand both are
Okay.
same are
Okay. First thing is I will clarify. Mechanical speed is not NR. I have used sometimes because you some different books use different symbols. So what I am writing, AFR is for the rotor frequency and corresponding to FR, NR is defined by this. This is the average speed of the rotor MMF with respect to the rotor. Mechanical speed, when I tell mechanical speed is this. Mechanical speed of the rotor, that is synchronous speed minus slip speed. I am writing mechanical speed of the rotor is the synchronous speed minus slip speed. It is the speed at which rotor is rotating. It is not this and that. But another speed, why we are writing mechanical, another speed also we define, that is called electrical speed. Electrical speed. Because you see, let us consider a two-pole machine. Two-pole machine, synchronous speed is 50 Hz. Considering 50 Hz, what is the synchronous speed for a two-pole machine? 3000 RPM. Now let us consider a four-pole machine. 1500 RPM. This 1500 RPM is the synchronous speed of the magnetic field. But we define inductive reactance. Let us say inductive reactance I am writing XL. Reactance due to unit. What is that? 2 pi FL or omega into L. Fine. You know that inductive reactance is 2 pi FL, that is omega into L. So what we write? Omega is the angular frequency, that is 2 pi F. Okay. Like so, and this omega is the angular frequency, and this omega also is linked to omega S. Omega S. What is that omega S?
2 pi
Yes, fine. You have already. So 2 pi into ns by 2 pi ns by 60. 2 pi ns by 60. Ns is the speed in revolutions per minute. Revolutions per minute. Divided by 60 is revolutions per second. Into one revolution is 2 pi radian. So this is radians per second. Now this omega S and omega, if we relate, it should be same, but it will not be same all the time. This is the 2 pi ns by 60. No, omega is 2 pi f, let's say. Another is this is 2 pi fs, supply frequency. So what is the difference? How do you compare? For a two-pole machine, this is thing omega s. N-S is 120 into F-S by P. The synchronous speed is 120 F-S by P. So what is omega S here if you substitute? Synchronous speed is 120 into supply frequency by number of poles. And omega S is 2. Omega S we are getting synchronous speed is the speed in revolutions per minute divided by 60 is revolutions per second. One revolution is 2 pi radian. So this is radians per second. So omega S if you substitute, that is 2 pi by 60, 120 Fs by P. So this comes 4 pi Fs by P. But this omega is 2 pi Fs. This is 2 pi Fs. So what is the difference? Suppose P equal to 2. Suppose for two pole machine, P equal to 2, this omega is 2 pi Fs. This is also 2 pi Fs. So no problem. But if omega equal to 4, this will be half of that. For 6 pole machine, it will be 1/3 of that. So there is a mismatch between omega equal to 2 pi f, which you use here in the reactance formula, and this synchronous. So mismatch. So for that we define called electrical speed. So this omega is the electrical speed. This is the mechanical speed. Mechanical. So in terms of synchronous speed, this is the synchronous speed mechanical. This is the electrical speed. Synchronous speed electrical. So similarly, mechanical speed also we define. This is the mechanical. This is the actual mechanical speed. Mechanical synchronous speed minus slip speed. Then also we define electrical speed. Electrical speed of rotor. That is
P by
yes, P by 2 into N mechanical. So that way we use mechanical speed and electrical speed.
Omega I is also equal to S into omega S. The angular frequency of the rotor is equal to slip times the angular frequency of the stator. That can be derived.
Both way you can do. Also, ये तो frequency alright. This is done. Rotor insertion. So if the rotor is rotating at synchronous, suppose in induction machine, rotor is rotating at synchronous speed. So what type of EMF is induced in the rotor?
Zero.
There is no EMF is induced. Its magnitude is 0, frequency is 0. Just before that, it is just like DC. This is nearly DC to 0. These are, while the input to the induction motor is the electrical power, the output is mechanical power. We should know the terms and quantities related to the mechanical power. One is torque and the motor shaft. This torque is output torque by mechanical speed. Power output, torque is torque into speed. So torque develop torque, load torque equal to output power by mechanical speed. What is mechanical speed? This is 2 pi Nm by 60. That you know. This omega is written in terms of radian per second, and small n m, that is speed in RPM, revolutions per minute. Then horsepower. All of you know horse is the main power that gave to drive the carts and all those things. Everything was horsepower. So horsepower is one important unit of power. In electrical, we use the power as watt. Volts into current is watts power unit. But conventional mechanical power they are distributed in horsepower. So there is a relation. Horsepower is 700 watts. So how it is come, that is different thing. We will not discuss. So this is a small example. This is, though it is a very simple example for you, we will just go through that. Just objects of mind refreshment. A 280 volt, 10 horsepower, 4 pole, 60 hertz. It is written 60 hertz. Let us take it 60 hertz. Star connected induction motor and the full load slip of 5%. What is synchronous speed of the motor? Please tell. First question.
It is 1800 RPM.
How anyone else? How you got it? Synchronous speed is 120 into frequency by number of poles. Frequency is 50 hertz. Number of poles is 4 pole. P equal to 4. Number of poles P equal to 4. F is 60. 120 into 60 by 4. So it is 1800 hertz. The synchronous speed. What is the rotor speed at this rated load? It is given
S into 1 minus S.
S into 1800. 5% into 1800.
Slip is 5%. Full load slip is 5%. Another thing, when the first sentence it gives a typical
90 RPM.
Right. So typical speed we write 10 SP means it is the full load torque. 10 SP is the full load torque. So this slip, full load slip is 5%. The machine either mostly defines the speed. Here it is not define the speed, it is define the slip. So slip means it is the full load slip. Slip is dependent on the load, it is not fixed. If the full load condition you get one slip, with no load you get another slip, with part load you get different slip. Okay. So full load slip torque is 10 horsepower, corresponding slip, full load slip is 5%. If full load slip is 5%, synchronous speed you got 1800 RPM. So what is the slip speed? S into 1800, 5% of 1800, that is 90. So full load slip speed is 90 RPM. Then the rotor speed is 1800 minus 90. So 1710 RPM.
In a single sentence you can, it is ns into 1 minus s.
Yes. NS,
ns into 1 minus
no. NS minus SNS. NS minus slip speed.
ns minus s ns. You can take ns common.
Then it is 1 minus S.
1 minus s.
That is fine.
That is the rotor.
That is the rotor.
Usually you are taking this in your classes.
That is fine. Everything is correct. How do you do? You write 1 minus S into NS or NS minus SNS.
Okay.
So you know slip speed is 90 RPM, synchronous speed is 1800 RPM. Both are correct. What is the frequency? What is the rotor frequency at this rated load?
S into
S into F. Yes. Fs is 60 Hz supply frequency. Slip is 5%. So it is 3 Hz. Rotor frequency is 3 Hz. What is the shaft torque or the shaft torque?
So that is the load divided by omega. 10 horsepower divided by omega.
So 10 horsepower means 1 horsepower is 746 watts. So power output is at 10 HP means 10 into 746. 7460 watts is the power output. The rated speed is corresponding to 1710 RPM. 1710 RPM, you convert it to radians per second. Speed is 15 radians per second. 1710 revolutions per minute. Divided by 1700 by 60 is revolutions per second. One revolution is 2 pi radian. 2 pi into 1710 by 60, that is the speed in radian per second. Omega m you got. Speed in radian per second.
So we are directly putting P divided by 2 pi ns in RPS.
Yes.
So
Not RPS, it is radians per second. No. Okay, why I told you are right. When you say RPS, it can be radians per second. R is also radian per second. So then student, other faculty members will not understand. But students will get confused whether it is revolution per second or radian per second. Sometimes we tell revolution per second. So radian per second is the correct answer. So this is what power out.
So here you are taking the PM divided by 2 pi ns by 60. This ns is in RPM, so you are converting it into RPS.
RPS.
So that's why you are getting the torque in Newton meter.
Newton meter. Then only torque can be written in Newton meter. Because power output is converted to watts. Then speed in radian per second. Then 1 watt equal to 1 Newton meter into 1 radian per second. Then equivalent circuit. Equivalent circuit. All of you are teaching machine too, so you know all those things. Just you are refreshing, nothing new. So equivalent circuit is there.
Directly that you, we have some confusion in torque slip characteristics.
Answer. At the equivalent circuit, anyone will go quick, slightly go to your torque characteristics.
Sir, it is called a rotating transformer. The induction machine is a rotating transformer, and a transformer is a static induction motor.
Yes,
They
definitely.
are equivalent.
So in transformer, nothing is rotating. Transformer, there is no rotation. There is a core and 2 windings are on 2 arms of the transformer. Okay. So when the stator primary winding, we don't have stator because there is no rotor. There is no rotor. Everything is stationary. So we don't have stator. Primary and secondary, what you use for the transformer. In transformer, in primary winding, we use supply due to that alternating voltage. one block is produced in the core, the transformer which is alternating. That alternating block is there in the core, and on the same core secondary winding is there. So secondary winding is linking with that alternating block. So EMF is induced in the secondary winding, that is due to d phi by dt, n into d phi by to the secondary also get alternating EMF.
Therefore, frequency is constant.
Frequency is constant. But in case of
Stationary.
phi,
Both are stationary.
that is very important. And in case of induction motor, it is similar thing. Primary winding means stator, secondary winding means rotor. But here rotor is rotating. Rotor is rotating. But
Therefore, frequency changing.
frequency changing. In transformer, both primary and secondary winding are fixed, not moving. But they are linked by one iron core. But in this case, transformer, in case of induction motor, they are linking through air gap. There is no iron core. Iron core is replaced by air gap.
Sir,
So that rotation can be
But
done.
all
Sir,
the
it can be compared with the transformer when the secondary winding is shorted. Yes.
and all the calculations and A stop will come into picture.
But sir, that whenever actually in transformer we are getting the humming sound because the second is trying to rotate, we are blocking it. Similarly, in the block motor test, we will get the humming sound.
That is also one important point you can always tell your friend. Transformer humming sound is there. Humming sound is there.
Because the second is trying to rotate, but it is not rotating.
And if you
Blocking it.
when in induction machine you block the rotor, it will produce sound.
Yes.
Humming sound. This is analogy also.
Sir, what is its fictitious reactance?
50. 50 TS reactance, what is that I am telling? So whether you discuss about, you can discuss with respect to induction motor or in case of alternator also, in case of synchronous machine also we use that both quick, here we don't write. So all of you know equivalent circuit of induction motor?
Yes.
Or anyone still wants some discussion? No, you don't want?
No, sir.
So this is the equivalent circuit of the induction motor. So right hand side, in both two circuits are separated by two. That is four. So yeah, four. So another thing, I will tell that point. I will before that I am telling. So suppose two windings are linking. Two windings, and sometimes we put two lines between that. Why we put lines?
It is four.
It is putting core. This line shows core. If lines are two lines are there, it is iron core.
Yes.
It is iron core.
Yes.
If two lines are not present, it is air core.
That is air.
Air core. And transformer is iron core. So in transformer, the primary and secondary were are separated by two lines. In induction motor, it is air core. So here two windings are there, and we are not showing by lines.
Lines.
Here lines are not there means they are separated by air core. And right hand side we have the rotor side, left hand side we have the stator side. So point was what is fictitious in the reactance? Anyone who can tell what is fictitious reactance?
Practically it is not present.
We want this
Physically not present.
dictionary meaning. Fictitious means it is
Imaginary.
imaginary. So we are imagining. So what is that we are getting? But still it is there.
Yes,
It is there. How it is there? So there are two inductances. So let us consider starter side. One inductance is here. Reactance. What is this? Why it is? What is it called?
Is that
Stator.
stator reactance? Stator reactance.
Stator winding reactance.
So when we are transferring something from the rotor side to stator side, then some anomaly occurs. And that anomaly is the fictitious reactance, because that S term will call and it will make it complicated, then it will be divided into two parts, real part and imaginary part. And in the imaginary part it is.
That is the 50 years.
Sir,
50 years.
In core or imaginary?
That is report. When you report, that part you have all of told, that is different thing. That is at 50 years. 50 years reactance we use in mainly alternator. So in induction machine we don't use, but induction motor also you can extend. That's why I told this reactance X1 here. No, sir. This reactance, this is one. You told it is reactance. So many of you told X1 is the reactance of the stator. What about XM?
Magnetizing.
It is of stator or rotor?
Stator.
It is in the stator. Then stator has one reactance here, another reactance here. Then now you are telling stator reactance. When you take stator reactance, when you tell stator reactance, does it exclude this one? Is it not in the stator?
Yes, it is.
So if you tell this one as stator reactance and still you are not including this one, then are you not doing some mistake?
Yes.
Both are there in the stator. But you told this is the stator reactance and you are excluding this one. But this is still in the stator. Then there some mistake is occurring. Both are there. Why you are telling one as stator? You see, out of these two, which one is more important? Yes, you tell me, X1 is more important or XM is more important?
XM is producing the magnetic flux.
Yes, that is the right point. That is the right point. Remember, you see, XM is the most important. First thing that will come is XM. If there is no XM, there will be no flux. How the flux is produced? One winding coil carrying a current produces flux. If winding the inductance is not present, there will be no flux. And without any flux, this machine cannot operate. So main operation is coming because of XM. Okay. So it is called magnetizing reactance. Because of the magnetizing reactance, the flux produced with which flux? Because of magnetizing reactance, flux produced. You know, stator has a flux, rotor carries a flux. Then there is a flux in the air gap. So, which flux XM refer to? One is flux of the stator, another is flux of the rotor, another is flux in the air gap.
It is XM is the air
Yes. XM is fine answer. XM is the flux in the air gap. I am drawing here. Now I am drawing about induction motor. So I am erasing the iron core. Some flux will link like this. Flux that occurs like loop. So this is the flux. Okay. Another part of the flux will be there, which is like this. And another part of the flux will be there like this. So three blue circles, blue graph circles. What about this one? This flux is linking with both stator and rotor. Please link. Flux always links with one winding. Flux linking with, that's why we tell flux linkage. Flux linkage means flux linking with the winding. This flux is linking with the primary winding, secondary winding of the transformer, stator and rotor of the induction motor. So if the flux is linking with both stator and rotor, then how it is crossing the air gap or not?
Yes.
Yes,
So
sir.
this is the air gap flux. Air gap flux, it is linking both stator and rotor. But another line which I have drawn here, it is linking only with the stator. It is not linking with the rotor. If the flux is linking only with the stator but not linking with the rotor, it is leakage flux. It is the voltage flux. It is the voltage flux, it is the leakage flux. It is not useful in power production. It is wastage, leakage. Similarly, another flux, this one which is linking only with the rotor, not with the stator, this is also wastage. This is rotor leakage. This is stator leakage flux, this is rotor leakage flux, and this is the useful flux or mutual flux or air gap
So
flux.
another one is also the fringing effect.
Hmm?
The fringing flux, the fringe effect.
There is another effect that. Okay. So now we have three inductances there. We have three inductances. One is XM. Okay. Now the XM corresponds to air gap flux. Another is X1. That corresponds to stator leakage flux. X1 corresponds to stator leakage flux. And another is XR. That corresponds to rotor leakage flux. Accordingly, XM is called the mutual inductance between the stator and rotor or magnetizing reactance of the machine, like that. X1 is called stator leakage reactance. Stator leakage reactance, and XR is called the rotor leakage reactance. So now when we say 50 TS reactance, so is combination of leakage reactance and the mutual air reactance. So it is the 50 TS reactance. Okay, we will have a short break. You can have free after that.
क्या बाबू हाँ बोलो
182 slide.
182
ଏବେ ଏବେ ଚାଲିଲା
ଏବେ ଚାଲିଲା।
ନା କହିଲେ ସେ ଷ୍ଟକ୍ ସ୍ଲିପ୍ ଡାଟା ସବୁ ଡାଇରେକ୍ଟ ଲିଙ୍କ୍ କରୁନ
Thank you.
सेकेंड आप मिल साउंड सिस्टम मिल हाँ सही सर जो प्रोग्राम गोटे पर डेटा
हो जाएगा, लेकिन जो हम बात रखें बात में अगर जरूरी होगा तो सब
विक्रमादित्य सर कोडिंग इलेक्ट्रॉनिक्स
ठीक है Siendo politización.
First hour and second hour. Streaming चलती वाले उनकी मैडम से फिट दक्षिण ଆଜି ଗ୍ରୁପରେ ଗ୍ରୁପ କରିଛ ସବୁ ଟପ୍ କରିବା ଏଇଥିରେ ବହୁତ ଯେଉଁ ଚାର୍ଟ ବହୁତ ନେଇଛି 96 88 ହେଇଗଲା ଚାରି ବହୁତ କମ୍ ଟ୍ରେକ୍ ହେଉଛି ଦିବ୍ୟ ଲ୍ୟାପଟପ୍ ଭଲ ଅଛି ଯେହେତୁ ଅଲ୍ଟ୍ରା ପ୍ରୋସେସର୍ ଅଛି ଆଇସି ଆସିବ ବସିବ ଖେଳିକି ପଳ ବାସ୍ ଖୋଲା ଅଛି ରେଷ୍ଟୁରାଣ୍ଟ ଦେଖ ଖୋଲା ଅଛି କାଲି ଥିଲା ଏଥିରେ କାଲି ଫ୍ରାଇଡ଼େ ଦିନ ଥିଲା KFCର ଅଫର୍ ବାୟ ୱାନ୍ ଗେଟ୍ ୱାନ୍ କାଲି କାଲି ଯେଉଁ ଇଏ ତ ରାତିରେ ବାହାର ଚିକେନ୍ ନା ଚିକେନ୍ ତଳୁ ଇଏ ନେଇଗଲେ ରୁଟି ସିଏ ଆଣିଲା ଜିନିଷ ବାହାର ହେଇଥିଲେ ସେଟା ମନା କରି
सेकंड हाफ में अच्छे मानव संग ଗୋଟେ କାଲି ଫୋନ୍ ସାଥି କାଲି ଆସିଲେ ତ କାଲି ସି କାଲି ଏ ପୁରା ଲୁଚି ଯେ ସୋ ଏଠି ବୋଲିକି ପାବା ଯେ ରିଆକ୍ସନ ର କରିଲେ એટલે આપણે ઉપર ମାନେ ପ୍ରୋବ୍ଲେମ સર કાલી
सेकंड हाफ
और पर ଆମେ ପବନ
ଏଇଟା ବହୁତ କମ ସମୟରେ ବନ୍ଦ କରିଦେବେ ନା ପୁରା ଚିରି ହେଇଯିବ ଥଣ୍ଡା ହେଇଯାଉଛି ନା ପଳେଇ ଆସୁଛି
ଆମେ ସବୁ ଚିଡ଼ି ବସି ଥଣ୍ଡା ହବ ବୋଲି ଆପେ ଗାଡି ଖାଲି ଆପଣ ଦେଖିଲେ ପୁରା ପବନ ମାରୁଛି ଆଉ ଜାଗା ବି ନାହିଁ ପୁରା ସେଟା ଭୁଲ ଜାଗା ଅଛି ସେଟା ଆଟେଣ୍ଡ ଅଛି ସେଟା ଗୋଟେ ଭୁଲ ଜାଗା
ସେଠି ଆମେ ऐसा आज दिन बस ए पूरा एमटी कॉल करना अपन ଥଣ୍ଡା ହେଇଗଲା यस लौट जाए
पूरा फुल करते देखिए ना स्पीड ऑफ वाला वो मुद्दा है वाला मुद्दा है
getting all the that
डॉक्यूमेंट पढ़िले पूरा क्वालिटी है माने एबे जे अपन भाषा पढ़ते हैं ये यदि कोई कोर्स के भी क्लास के भी डॉक्यूमेंट चाइल्ड पार्ट एमबी दे
चल रहा है
इसको पहुंचेगा नहीं ना लोगों की जो मैंने पोस्ट किया था ग्रास
साढ़े 12
वो तो मोटे दिन देखिए अरे ये देखिए पूरी
सुनना बच्चे से ठीक है बस हेल्मेट तले सिक्योरिटी हेल्मेट पाकर जोड़ी सिक्योरिटी बस ग्राउंड फ्लोर बोले वाईफाई वाला तो वाईफाई कंपैटिबिलिटी तो वाईफाई से देखो ना
बहुत से अनुरोध
कितने वाईफाई से तो वाईफाई कंपैटिबिलिटी
प्रोजेक्ट के लिए होता है नहीं बहुत ज्यादा प्रोजेक्ट को
सेट वाईफाई रे कनेक्ट कर काली चला काली 749 दिला
के करना है आपको के लिए शेयर बटन कोई नहीं उपलब्ध होगी
कितने से उठे सुबह 749 दीदा भी नहीं सर
करेक्ट में नलो के काम को कोई काम मिले आपको ये आपको कोई काम कोई सेम बात है आपको कोई आपको
सुनो गाड़ी है
काम बता दो सुन काम
रोज ही मिल गई
तो बिस्कुट
तो नहीं है मुझे तो चल रहा है तारा नंबर नहीं मना ही कर रहे हैं भाई थोड़ा
Before that, we discussed 50 days reactance. Yes. That part is in induction motor we don't use 50 days reactance frequently, but alternator it is fixed. In alternator, here in alternator this XM what I told that will be there the armature reaction reactance. Alternator armature reaction reactance. That part is for the armature reaction part. Then this is leakage reactance of the stator. Combined is the synchronous reactance. That is the synchronous reactance. Then this armature reaction reactance part is called the fictitious reactance. Okay, that part is there. This part also we have already discussed because in the beginning we told rotor induced EMF when the rotor is not rotating, sleep is 1, induction rotor. When the rotor is not rotating, sleep is 1. EMF induced in the rotor is maximum because relative speed is maximum, synchronous speed. So that EMF is ER0 in this equation. This right hand side ER0 is the that EMF. Then when the rotor is rotating with a sleep S, then the relative speed is S times the synchronous speed. To induce EMF becomes S times ER0. That at any sleep S, EMF is ER, that is S times ER0. Similarly, frequency, but synchronous frequency is AP. That is also frequency when rotor is not rotating, sleep equal to 1. When the rotor is rotating at sleep 1, rotor frequency is S times.
Sir, in previous slide, equivalent circuit one denotation is A effective. In between A, what is that? AEF.
No, this one, no, this one.
Yes, sir.
This is for Town's ratio.
Town's ratio.
Town's ratio.
Oh, yeah, yes, sir, yes.
How it is coming? Okay, if you have asked, because I want to tell. Just like transformer,
Yes, sir.
here we write rotor induced EMF is E2, then stator induced EMF is E1. The ratio is N2 by N1. Okay. And that is also nearly equal to ratio of I1 by I2. So that N2 I2 is nearly equal to N1 I1. MMFs are nearly equal. And this ratio, if you write, that is the they are writing effective. So okay, they are not necessary to write. Okay, I am writing according to slide effective. Then what? This is the ratio, Stone's ratio. Then because EMF ratio is this, what is ratio of Z2 by Z1? Z2 by Z1. Stop. The impedance.
Yes, sir.
Z1 is the stator impedance. Resistance one part and reactance another. Similarly Z2. So Z2 is how it will come? It is V2 by I2 and this is V1 by Z1 is V1 by I1. So this is equal to V2 by V1. V2 by V1 into I1 by I2. So V1 by V2 is A effective. This is also A, so it becomes square. Okay. So Z2 equal to Z1 into A effective square. Okay. So when you refer Z2 with respect to stator, Z2 dash, rotor impedance refers to stator, that is also equal to that is equal to Z1 into you see Z2 dash, Z2 you can write X2 dash equal to X1. X2 dash equal to X1. So if X2 dash equal to X1, X2 dash is
total reactance support to primary side or stator side.
X2 dash is the rotor reactance referred to stator side as rotor side referred to primary side. X2 dash equal to X1. So because X2 dash equal to X1, this is X2 dash equal to X2 into
Plus X1.
here it is not Z1, here it is Z2. So this is X2 dash equal to X2, you are referring X2 to primary side, stator side. So you multiply this ratio square, so that it is X2 dash and X2, now you can say X2 dash, this equation is satisfied. Similarly, other term, resistance, impedance. So similarly, you get reactance, everything. Job rotor characteristics are 0, you are getting equivalent circuit. Okay, now equivalent circuit, all of you know, there is nothing new, just brief refreshing. So we start from a stator, or rotor. So induction motor, rotor. So induction motor EMF is induced, and that EMF is alternating, and because it is a winding, it will have some resistance. So the rotor winding has a resistance. This is the resistance. Then reactance. Reactance in induction due to that is coming. It will have a S multiplier. Why it will be S multiplier? Because frequency is multiplied S times. Reactance is multiplied S times. And this EMF is also multiplied with S times. Because EMF is proportional to relative frequency. Okay. Now this is the equivalent circuit. At any slip S, EMF is S times the starting EMF. The frequency is S times the starting frequency. So reactance is S times, but resistance is fixed. So now we convert it to stator side. So how? What is the rotor current? Rotor current equal to EMF by resistance plus J times reactance. So this reactance, the EMF is S times starting EMF, resistance is same, and reactance is S times the starting reactance or starting resistive frequency. Now you divide both by numerator and denominator by S. So you get ER0 divided by RR by S plus J. This S we have divided in the denominator. So now to the rotor circuit which we have drawn in the previous slide, we can make it equivalent by how will make it equivalent? We will keep this EMF, starting EMF, the resistance is divided by S times and reactance is starting reactance. So this way we are drawing the equivalent. This condition refers to slip equal to 1. This equation refers to slip equal to 1, slip equal to 1, this is 1, so this is resistance. At any slip also it is applicable. So we will refer to the equivalent circuit. For required circuit, we get that. So this is the modified equivalent circuit of the rotor. Now we take it to the stator. So this is the total equivalent circuit of the stator. Just refreshing, nothing new. You know all these things. So this Thomas ratio also they are defined with the whatever I told. Then power loss. Power loss, there is copper loss in the stator, I square R loss in the stator winding. That is I square R loss in the rotor winding. Then there is core loss. Then mechanical power loss will be there because friction loss will be there. So these are the power losses. Okay. So how the power, first power input comes, power flow. Power comes to the input power is in root 3, line voltage, line current, cos phi, power factor. Root 3, line voltage, line current, power factor. This is the input power. After the input power comes to the stator, there will be stator copper loss, I square R loss in the stator winding. Then also there will be stator core loss. After the total loss, power crosses the rotor. This time is air gap. So power crossing from stator to rotor via the air gap is the air gap power. Then after the power comes to the rotor via air gap, then there will be rotor copper loss. Then there will be some rotor core loss also will be there. It is not shown here because core loss here, rotor core loss is included, but otherwise rotor core loss also occurs at this point. Then we have some friction and windage loss and stray load losses. Then we have power output. Then equations for the power. These are the input power is P input 3 V phase I phase voltage phase current into power factor or 3 line voltage line current power factor. And SCL is stator copper loss for 3 phases 3 times I square R. For the air gap power, input power minus stator copper loss and core loss combined. Then rotor copper loss this much, I3 I2 square R2. Then we have the power converted power, air gap power minus rotor couple loss, then the output you get after subtracting friction and windage loss and straight load loss, then the torque in this power by mechanical circuit. Then the equivalent circuit, we can rearrange the equivalent circuit as follows. That is same thing which we have discussed. So the rotor resistance was active by S at statical condition or at any slip S. The rotor resistance is active by S. Now that is separated into two parts. One part is actual rotor resistance which is present, and this part is the load resistance which is equivalent. Actually, the motor shaft load is mechanical load. Okay, but equivalent circuit we are drawing, it is electrical equivalent circuit, this is resistance inductance. Then how do you represent the actual mechanical load on the shaft in the electrical circuit? In electrical circuit, only thing which can dissipate power is resistance. Load is basically taking the power, dissipating the power, mechanical load. But in electrical circuit, load is the resistance which can dissipate power. So the mechanical load of the shaft is represented by equivalent resistance. This resistance is the equivalent to load resistance. Shaft load is converted to this, and this is the winding resistance that represents the rotor copper loss. So tri-square loss is represented by this resistance, and this is the shaft load. So equivalent the resistance equivalent to shaft load, mechanical load. So otherwise there is nothing new, and this is the equivalent circuit. Power relation. Same thing in different way, and power relation that is air gap power, the rotor copper loss. Then you have converted mechanical power on minus S times air gap power. So the ratio is like this. This formula is very often used. You can remember. So air gap power is 1 unit. The rotor copper loss is S. Then S times the air gap power. And mechanical power or converted power is 1 minus S. 1 comes, then S is the loss, then 1 minus S is the output, mechanical power. Then this is a simple example which you have already done, means you have done solved a very difficult problem. This is a very simple problem, but still have a memory refreshment. Just work out this on mind. If you want, you can use your paper there, otherwise you can solve this. 480 volt, 60 hertz, 50 horsepower, 3-phase induction motor is drawing 60 ampere at 0.85 lagging power factor. The stator copper losses are 2 kilowatt and rotor copper losses are 700 watt. The stator copper losses and rotor copper losses are given. The friction and windage losses are 600 watt. The core losses are 1800 watt, and the strain losses are negligible. And the following percentage. Air gap power. To tell how to get air gap power.
Starter input minus starter copper losses, that is air gap power. Input to the starter minus copper loss. Starter cos phi minus I square R, that is into
rotor stator couple loss is
VI
given 2
cos
kilowatt
phi minus the stator loss.
VI cos phi minus 2 kilowatt.
So that is output by efficiency we can find our input. If the output is there. So efficiency is not given, na?
Efficiency is not given. Efficiency is not given.
Okay, output power is given. Output power is given. Root 3 into input is given. Root 3 VLIL cos phi we can calculate minus 2 kilowatt if we get.
Current is given and voltage is given.
For that from PAG we have to subtract rotor copper loss and friction and windage loss.
But
So loss
current is not
get
given.
reconverted.
Sir, current is not given. You have to divide 50 H power divided by root 3 VM cos phi. That will give you a current.
No, input current
No,
is
input current is there. Na?
Input current is given 60 amps.
60
Okay,
ampere
then
and
that's it.
voltage V1 480. Cos phi is 0.85.
Next thing is you have to get the input power. Input power is root 3 line voltage, line current into power factor. So line voltage is 480 volt. Line, whenever nothing is mentioned, line voltage, phase voltage, star connection, delta connection, remember whatever voltage is given, line voltage,
Sir,
line current.
internship.
Okay, if nothing is given, you take that line. So line voltage, line current. So line
Since
voltage
when,
is
sir?
480 volt, line current is 60 ampere, and power factor is 0.85 into root 3. These things product gives input power. You got the input power like this. Then loss. We want air gap power. Before air gap, we have what are the losses you get after the input power? What are the losses to be subtracted minus so that you get air gap. Stator copper loss and stator core loss. Both after subtracting you get air gap power. But here core losses are 1800 watt. So how much is stator copper loss? How much is rotor copper core loss? Not given. Stator copper loss is given 2 kilowatt. Stator copper loss is 2 kilowatt. That will be definitely subtracted. But rotor copper loss is given. No. Stator copper loss is 2 kilowatt. Then core loss is given 1800 watt. Means stator copper loss plus rotor copper loss. Stator core loss plus rotor core loss. Combined is 1800 watt. So how do you get?
Sir, then 2 kilowatt plus 18 kilowatt, 1800 watt will be subtracted from the input power. Root 3 VLI. Say, इसको subtract
Because rotor core loss is neglected.
Rotor core loss is rotor.
Rotor?
Core loss is neglected.
Why?
Because the frequency is less.
That is the right answer.
Yes.
This is the point. This is the point. Actually, in this case, you cannot get exact thing. You will not get because how much the total core loss is given 1800 watt. Out of that, how much is stator core loss? How much is rotor core loss? We cannot separate. We cannot divide. So we can, but we can do an approximation, which is the best approximation based on the data that we have to use. Not that exact, whatever data is given, according to that you have to get. So stator core loss plus rotor core loss is 1800 watt. Out of that, the rotor core loss is negligible because core loss depends on frequency and flux. Okay. As in rotor, frequency is very less. Slip times the supply frequency. So say supply frequency is 50 hertz. So rotor core loss will be, stator core loss will depend upon 50 hertz. But slip is hardly becomes 5%. Slip 5%. So 5% means rotor core loss at 5 hertz will be 1/10 of the rotor core loss at 50 hertz. That means 1/10 of the rotor core loss at 50 hertz, stator core loss. So because of that, because slip is around 5%, the rotor core loss is around 10%. So 10% you can neglect because full data is not there. So rotor core loss we will neglect and total 1800 watt will take as stator core loss. So 2 kilowatt and 18 kilowatt combined subtracted from the input power, you will get
Air gap power.
air gap power. Then the power converted. Power converted means mechanical power. Mechanical. The first bit you got the air gap power. Then what, which loss to be subtracted so that you get mechanical power. Only rotor core loss. Because rotor core loss you have already subtracted. Only stator rotor copper loss it will be subtracted. That is how much? 600 watts. No, not 600. No, that is 700 watt. Only 700 watt is the rotor copper loss that will be subtracted from air gap power. You will get mechanical power. Then output power you will get
Minus
additionally 1800 watt is to be subtracted. And efficiency. Efficiency is P out by P in. Output power by input power is the efficiency. This way it is solved like this. Same thing. Same thing.
18.
Another example you work out. 460 volt, 25 hertz power, 60 hertz, 4 volt, star connected induction motor has the following impedances in ohms per phase. The total rotational losses are 1100 watt, but are assumed to be constant. Core loss is along with the rotational losses for a slip of total rotational losses and assumed to be constant. Core losses is lumped in the rotational losses. slip of 2.2%. So now we find out rotor slip is even 2.2%. Speed, what is the part 1, what is the speed? How do you get speed?
First find out NS.
NS.
NS into 1 minus S into rotor speed.
That is what? NS you will get 120 F by P. F is 60 Hertz, P is 4. So 1800 RPM is the synchronous speed. Then slip is given 2.2% with 0.022 is the slip. So speed is 1 minus 0.22 minus S into NS, that is 1800 RPM, you will get speed. Then stator current. Stator current, how will you get?
Input voltage divided by stator resistance plus stator reactance square.
XM is also there.
So that will be the.
You will use the equivalent circuit. You will use the equivalent circuit to determine the stator current.
Secondary side refer to
So equivalent circuit will have all the resistances. You have got the slip value S 0.022. Then R2 by S. This is R2 divided by S is one resistance. Then X2 dash. These are all R2, X2 means refer to stator it is given. R2 means R2 dash, X2 means X2 dash. Actually refer to stator.
X2 by S.
X2 dash, X2 means X2 dash. It is given refer to stator. So R2 dash, X2 dash you got. Then R1, X1 is there. XM is also there. Using the equivalent circuit, you will get stator current. Total circuit equivalent circuit. Then power factor. What is power factor? From the equivalent circuit you will get phase angle between the input current. How for input current you will get the total impedance Z. So impedance has an angle. That angle is phi.
Otherwise, sir, resistance divided by impedance is also power factor.
That is one. Yeah, fine. That is one.
R divided by J into power factor.
Same thing. That also you do. From the total equivalent circuit, the total impedance equivalent impedance is R plus Jx. That is Z. So power factor is R by R square plus X square whole. That is the power factor. Then convert mechanical power and output power. Mechanical power you will get like this. You got the stator current. So input power factor. So input power is √3. Input voltage VL is 460 volt. IL you got using the equivalent circuit into cos phi. You got input power. Then out of the input power, you subtract the total rotational losses 1100 watt and also I1 3 I1 square R1. 3 I1 square R1. That you get plus I2 square R2. 3 I2 square R2. You get mechanical power. Mechanical power. This you tell mechanical power. Then you supply this P out. Actually, rotational losses will be subtracted at the end. That you can do. Core loss. What is core loss? Is along with the core loss is along with the rotational losses. You see, in this case, core loss and rotational losses are combined. So it is better you subtract from the input power. Because you cannot supply a separate core loss and another one is rotational loss.
See dot.
Rotational losses are usually smaller. Rotational losses are small compared to core loss.
Double E.
So because core loss, stator core loss is major part, it will supply, it is subtracted at the beginning. So P out then you will get and the torque you will get and load, torque induced and load torque. Load torque is the mechanical power. Load torque here this is a load torque. How do you get? Corresponding to 25 HP. 25 into 746. That is the power output. Divided by speed. Speed is given how much? Slip is given.
NS.
No, NR sir. NR.
This one or
This one we have done.
here. Slip is given 2.2%. So NS is 1800 RPM. So speed you have got here. So speed is that is mechanical speed into 2 pi by 60. That is the speed in radian per second. And P out 20 SP into 746 by that speed is the load torque. Then induced torque is this P converted by 2 pi n by 60. And efficiency you will get by output power by input power. Is it okay? Just convert. So you got synchronous speed, then mechanical speed, then Z2. That is what I was telling. You have to do the equivalent circuit analysis. You just Z2 is R2 by S plus JX2. R2, X2, the sleep and X2. So you got like this. Then ZF you got total, that is this 1 by Z2 means Z2 and XM are in parallel. Your core loss we are not considering. So core loss by separate. So we are considering Z2 and XM in parallel. So you got ZF. ZF you got by this equation, then total impedance is Z total plus ZF. So you got total input 36 like this. So impedance is now 14.07 and power factor is cos 33.6 and I1 is V by per phase voltage by Z. Per phase voltage is root 3 into whatever 460 by root 3. 460 by root 3 and Z is 14, magnitude is 14.7. So you got current. Power factor you got and input power is root 3 VL IL cos phi. You got input power is like this. So stator core loss you subtract. Stator core loss is also given like this. And air gap power is this much. Stator couple loss subtracting you got. Converted power is 1 minus S times air gap power. So you got mechanical power. And output power is subtract friction and windage loss. So torque you got air gap power by synchronous speed. Torque is another way induced torque. Induced torque we also tell electromagnetic torque. Electromagnetic torque is air gap power by synchronous speed in radian per second. That also it is there. And load torque is P out by mechanical speed. Efficiency you get P out by P in. Then torque, power and Thevenin's theorem. So that is what Thevenin's theorem we consider how this R2 by S we consider as the load resistance because R2 dash by S is sum of two parts. One is the actual rotor resistance, winding resistance and shaft load converted to resistance. So both are combined and in the equivalent circuit, in the equivalent for Thevenin's equivalent circuit part, this R2 dash by we consider as the load resistance and remaining whatever is there we convert it to Thevenin's equivalent circuit just like you do apply Thevenin's theorem. Then V Thevenin and like that you got that Thevenin's equivalent circuit. You keep R2 dash by S as the load resistance and remaining part you see. Then you can use back when the power will be maximum, torque will be maximum. When the torque developed will be maximum. When power transfer to this resistance is maximum, torque is maximum. How when the power transfer to this resistance is maximum?
Resistance will be equal to reactance.
This is equal to total impedance. Square of this plus square of this to combine whole root. When this happens, power is maximum. Torque is maximum. So that way you do Thevenin's equivalent circuit and get some approximation we do by neglecting the stator leakage reactance. So this X1 is, so this way you get do some simplification to get Thevenin's impedance, voltage and current, voltage and resistance. So this way you can go torque and power. Torque is I2 by V Thevenin by Z system impedance, and so you get power, internal mechanical power. So these are our Thevenin's equivalent circuit based analysis. Now torque speed characteristics. You were someone asked regarding the torque speed characteristics. You have some doubt. Who asked torque speed characteristics doubt? You are. That we are going to discuss. This is the point we are discussing. That we will ask.
Real is the meaning? Stray loss. What is the meaning?
When there is no load, this loss occurs due to some uncommon factors like core loss. Core loss is we know that core loss occurs because of this. Copper loss we know I square R loss. The stray load loss means it is a loss when the load is not there. It is some like it is not mean rotational loss. Rotational loss, friction windage loss.
I mean, that one is effective one.
It is there. It is there. Loss is there.
And in the body, in the body of the York, some EM will induce. So that eddy current loss, that is called.
That is a fine point. So core loss we are telling. When core loss we are using stator core, rotor core loss. But in the yoke, some flux reversal is occurring cycling. There will be some yoke loss in the yoke, but we don't consider it in core loss. It is in stray load. Yoke is there, na?
Physical support.
Out of the motor.
In transformer tank also the same loss is there in the transformer tank. The tank will also cause some loss. That is status. In transformer. So actually I have a doubt in this speed control of induction motor. One method is there in the rotor which can inject the voltage and control the speed. In that method, can you round the motor at synchronous speed also?
Yes, definitely.
So that I will doubt. That is we cannot say that the induction motor will not round at synchronous speed. It can round at synchronous speed.
It cannot have synchronous speed.
Like that method.
Even it cannot have speed more than
Yes.
synchronous speed by that method. Time permanent. Either today or tomorrow, we will discuss it. It may be sometime at the end of the that is what I understand. How
Sleep speed torque कमी गेला ना आता स्पीड कमी
is the
जीरो लेवल स्पीड
torque versus speed graph of the induction motor. So at this point, speed is x-axis is the speed, y-axis is the torque. At this point, speed is 0. Motor is starting. Motor is starting. We have applied voltage, and motor draws the current. And because of the power input, voltage current, there is some power out input, and because of the power input, there it will correspond to a torque. Though it is not rotating, but power input is there. So electromagnetic torque is developed. Power by, so that is the torque because of the input power. So that is the starting torque. Because of the starting torque, it rotates. Because of the starting torque is there, electromagnetic torque, so torque is there. So it rotates. And because of the rotor initial part, the speed is increasing and torque is increasing. Speed is increasing, torque is increasing. Usually, when we say, when you increase the torque, speed should reduce. It should reduce. If you are increasing the torque, it should reduce. But in this case, speed is reducing, torque is reducing. What is the reason? Whatever may be the reason is, it is an unstable part. It is not a stable part. Or non-stable part.
The torque means a load torque. Load torque.
Load torque. This is electromagnetic torque. Electromagnetic torque. So this part both. This is electromagnetic. If you apply more load torque, then only speed will reduce. But in this case, whether load is there or not, we don't analyze that. But speed is increasing, torque both are increasing. That means power, it is drawing more power. Okay. Power increasing, drawn is increasing. But this part only it quickly passes through. From here to here, it is a unstable part which quickly passes through the motor. And after this point, the speed is, it is the maximum torque is developed at this point. After that, this part is the stable region, and finally motor rotates at a speed given by this point, and this is the torque. This is the load torque, and this is the corresponding point.
The y-axis, what is it?
Huh?
Y-axis?
It is the torque.
Torque.
Electromagnetic torque.
So at mechanical speed 0, the torque is 200.
The full load torque is 100, that is the
Yes,
full load torque is they have taken, I think.
Full load torque is 100%, rated torque, okay. Rated torque,
Torque is 100%.
full load torque, rated torque is 100%, but at starting, motor draws more current. Rated torque corresponds to rated voltage and rated current. Just listen. Rated torque corresponds to rated voltage, rated current input, but at starting, induction motor draws a current which is 5 to 7 times the rated current. To directly switch on the motor to the supply, it will draw a current, starting current which is 5 to 7 times. Okay. So accordingly, torque will be very large. So for that, it is starting from 200%. Okay. And after that also it quickly accelerates. Accelerates means speed increases, and in the process, the torque is also increasing. And finally, it quickly achieves the point where the maximum torque is developed, and after that, based upon the rated load torque, it operates at a particular speed. This part is only the from maximum torque. This part is only stable region. This part is unstable region. Alright. Comments. The induced torque is 0 at synchronous speed, that you have discussed. The curve is nearly linear, but no load between no load and full load. That I have discussed initial part. In this region, the rotor resistance is much greater than the reactance. The rotor current torque increases linearly with the slip. The maximum possible torque that can't be exceeded. Maximum torque, this torque is called pull-out torque. And it is 2 to 3 times the rated pull-out torque. The starting torque of the motor is slightly higher than its full load torque. The motor will start carrying any load it can supply at full load. The torque of the motor for a given slip varies as the square of the applied voltage. If the rotor is driven faster than synchronous speed, it will run as generator, converting mechanical power to electrical power. These are some photographs. So this part is the torque.
Sir, in the generating mode, the shaft is rotating more than the synchronous speed, but
Yes.
it is transferring to the grid.
Yes. Because speed is more than the synchronous speed, slip is negative, and speed is more than the synchronous speed, and power is negative. Power is negative. The motor power flows from the grid to the motor. Now it is flowing from the motor to grid. Generator. Maximum torque, that part is maximum torque, as I told, the resistance. The slip at which maximum torque occurs is given by Ft max, and at that point slip, resistance is up to by S max, and that is equal to total impedance. Thevenin's resistance square plus Thevenin's reactance plus X2 square added, and total load occurs. So maximum torque occurs at the slip given by this. The maximum torque from the same expression, by substituting the slip S max, you get this is the maximum torque. Slip at maximum torque is directly proportional to the rotor resistance R2. Maximum torque is independent of R2. The value of maximum torque remains unaffected, but the speed at which it occurs can be controlled. Then in a squirrel cage induction motor, the rotor terminals are not accessible, not available, and we cannot change the rotor resistance. It is fixed. But if it is a slip ring induction motor, rotor terminals are available, and we can add extra resistance through after slip rings. So rotor resistance can be increased. If you can increase the rotor resistance, the torque slip speed characteristics are modified. So this is without any extra resistance in the rotor. This is the torque speed characteristic with the R1. Then you go on increasing the resistance, total resistance becomes R2, total resistance becomes R3, R4, R5. The torque speed characteristics are modified like this. So what happens? The slip at which maximum torque occurs increases with increasing rotor resistance, and the power input starting torque also increases. But after a certain point, starting torque also falls. Then there is a numerical, you can always solve from numerical from the book in that book. And then motor parameter determination. Induction, how do we determine motor parameter? First thing is we have to determine the resistance of the winding. Determining the resistance of the winding, we do DC test. Because when we apply DC machine to the machine, the reactances will not be effective. The inductance will not be there because of DC, reactance of inductance is 0. So reactance will not play a role. So you will get resistance only to determine the stator resistance. Then we do no load test and the block rotor test to determine the equivalent parameter. In no load test, basically it is called open circuit test. Okay. There is no load. No load means we consider R2 dash by S as the load resistance. R2 dash by S is the load resistance. If there is no load,
So no load means no torque, zero torque.
Okay. So no load means 0 torque. Power output is 0. And so what is this resistance? R2 by S. R2 by S is the equivalent resistance. Slip is 1. Slip is 1 means this resistance value is minimum. At no load condition, no load speed is maximum. No load speed is maximum. With load speed reduces. So no load speed is maximum. S is minimum. No. That is for S equal to 1 at standstill condition. S is 1 at standstill condition. At no load condition, motor is rotating at maximum speed. Maximum speed. So slip is nearly equal to 0. Sorry. Slip is nearly equal to 0. If slip is nearly equal to 0, then this is infinity. Infinity means open circuit. Open circuit means no power is going to there. So it is open circuit test. Open circuit test or no load. So with that, because it is open, rotor current is 0. Rotor current is 0. Stator current only small current is drawn due to the magnetizing current. Stator current is only due to the magnetizing part. So I square R losses are negligible. So in this no load test, we determine the reactances of the stator, that is X1 and rotor X2 dash. This is no load test. Then we do locked rotor test or blocked rotor test. In blocked rotor test, we are not allowing the machine to rotate. So in the blocked rotor test, S equal to 1. If S equal to 1, R2 by S is R2. So this is the minimum value of resistance that can occur. S equal to 1, this is the minimum value of resistance, because when S reduces from 1, it reduces, the resistance increases. Resistance increases means current increases. So this is the at S equal to 1, resistance is minimum, so current is maximum. Current is maximum, so I square R losses are mainly dominant, power more dominant. I square R loss. So core loss is negligible. And in block rotor test, because resistance is minimum, with a small voltage, the current will be large. So we don't have to apply the full voltage in lock rotor test. We lock the rotor, we don't allow it to rotate. We apply small voltage so that only rated current is circulated. For that we apply small voltage, rated voltage. So because voltage is small, core loss depends upon voltage square. So because voltage is small, core loss is also negligible. Core loss is negligible, so losses occurring is merely I square R losses. So you determine stator parameters, resistance parameters R1 and R2 dash. Here also you determine XM, magnetizing reactance in no load test. That is part of our DC test. I have told like this. So suppose machine is star connected. DC test I am telling machine is star connected. So star connected. You keep one terminal open. So now two windings. You apply connect to a DC voltage, DC source, voltage source. You connect a voltmeter and ammeter like this. So this voltage by current, DC voltage by DC current gives the resistance. Resistance of two windings. Two windings R1 and R1. Two R1 you get. Voltage, this voltage is shown by the voltmeter divided by current shown by the ammeter equal to total resistance, that is 2 R1. Divided by 2 you get R1 through DC test. Then same thing, and if the starter is delta connected, you will get total resistance is 3 by 2 into R1 total. And no load test you do like this. In no load test, there is no shaft load, but we apply the full voltage and we connect wattmeter to wattmeters like this, and one ammeter we also do. 3 wattmeters are not required. 1 voltmeter, 1 ammeter, that's 3, and 2 wattmeters. VIW are getting. So you get no load voltage. This was no load voltage, line voltage, and this is the no load current, and this will give no load losses.
Sir, what is the amount of voltage across before the slide?
Previous slide, no?
Previous one.
We apply DC voltage, small DC voltage we apply. This is DC voltage, we apply only small DC voltage, but you have to keep in mind this current should not exceed the rated current. It should be equal to rated current. So we apply start from 0 voltage, slowly increase so that this current becomes rated current.
What is the amount of DC? Small means
9 volt.
Maybe 10-20 volt may be necessary. It will vary from point machine to machine. It is not clear, but it is around that 10-20-30 like that.
Multimeter also you can directly measure that.
Multimeter also you can vary, but multimeter you apply only 3 volt or like that. With that small voltage, you don't get accurate result. But still it can be done. But you have
After that, whether you have to calculate with AC resistance, 1.6 you have to multiply.
AC resistance, okay, that's what I have not told. So in DC, whatever resistance you get, in AC the 50 Hz resistance will be more. Why it will be more? Who can tell?
Because of the scale effect.
Because the scale effect resistance will be more. If the frequency still increases and increases, resistance still increases. Okay.
Because of the
Frequency. At higher frequency, resistance is again some deeper analysis is required. Why the resistance increases with frequency? Some deeper analysis. Though it is not there in this course. Let me see it and we can discuss. No problem. So just think and tell. Now point is, if the resistance is higher, frequency is higher, the resistance increases with frequency. Why? Think and tell, let us have a
AC resistance.
Now that the inductive reactance will be more, so the resistance part will be less. Current will move in the outer side more.
Exactly, this is the correct point. That is what I want everyone should know. He knows, but all of you, what is your name please again?
My name is Sivanand Misra.
Sivanand?
Misra.
Where are you working?
I give problem. Give Bhubaneswar.
Give to home, sir. Gandhi Institute, no? And who is HOD?
Now, I was actually says Bhavani Patnaik is there. Before that actually.
Your name would, one person contacted gift, na? I am forgetting everything. Okay. The point is that when you apply DC, the inductance will have no reactance. Inductance will have no reactance. Okay, because frequency is there. When you apply AC and you go on increasing the frequency, the inductance will increase with frequency. And whenever you make a resistance, it will have some inductance also. Okay. So because of this inductance, the reactance increases. Because reactance increases, the current tends to flow more and more on the outer surface, not in. Suppose this is a current. This is a current. If you apply the direct capacity, direct current, the current will be uniformly distributed along the cross section. So you take total cross sectional area to find the resistance of the conductor. When you apply AC, because of higher frequency, from the reactance increases, so current does not flow in the center. Current flows only in the outer surface, not in the inner core. So very high frequency it will flow only at the surface only, not total inner will be useless. Okay. So in that case, effective area of cross section of the conductor reduces. Though actual conductor is solid, but current is not flowing in the inner core, so it is of no use. Effective area is only considering the outer surface. So because area of cross section increases, the resistance becomes higher.
Area decreases.
Area of decreases.
It is rho L by A
Resistance is R equal to rho into L by resistivity into length of conductor divided by area of cross section of the conductor. When the frequency is higher, area of cross section, effective area of cross section of the conductor reduces. So resistance increases. So AC resistance is higher than the DC resistance. It is not always 1.1 or 1.2. It depends upon the frequency. But considering 50 Hz frequency, it is around 1.2, 1.15 or 1.1, some 1.1 or 1.15 or 1.2 within that range, 1.1 for 50 Hz. But if the frequency is say 10 kilohertz, resistance will be very large. Multiply factor is not 1.2. Okay, so that's why in DC test we measure, apply DC voltage, that and we measure the resistance. So for effective R1 we multiply factor 1.1 to 1.2. हो गया. The no load test, that is what I have explained. Basically, no load test. No load test means machine is not operating at maximum speed. If there is no load, speed will be maximum. That is near to synchronous speed. Near to synchronous speed. So sleep is nearly equal to 0. Sleep is nearly equal to 0. So after it, this is.
But machine will draw current. Machine will draw current.
Machine will draw current because rotor part current will be negligible.
Only because of the friction.
Magnetizing current. Magnetizing current it will be there.
And only if the torque will be frictional torque and all those things. Load torque is 0.
Load torque is 0. Frictional torque is also that is very small. High.
Due to core loss, sir.
Due to
current.
Core loss will be there. Core loss part it will be
The
there.
core loss.
The predominant loss in no load test is core loss. So that part is over. So no load test I have already explained. So no load losses in no load test, I square R losses are negligible, and still you can subtract it because in DC test you measure the resistance and you find R1 after multiplying 1.1 you have measured resistance. So what you can do? The no load test you use two wattmeters to find the total power input. If you have determined I1 and you have seen the wattmeter reading, ammeter reading, then you can subtract I square R losses, copper loss. And remaining thing is the core loss. Friction and windage loss you neglect. So core loss you determine, you get Xm and exponent X2 dash. No load impedance. No load impedance is whatever voltage you have applied divided by no load current. That is no load impedance. Because the resistance is negligible, so it is X1 plus Xm it is written, or otherwise you can, what you can do, you can, I will draw the equivalent circuit here. It was there. So this is the no load, you have a stator resistance, you have a stator leakage reactance, and this is the magnetizing reactance, and so this is the equivalent circuit at no load. equivalent circuit. You have applied the no load voltage V1. You have measured the no load current I1. Okay. This is R2 dash by S is nearly equal to infinity. Open circuit test also we tell. So because open circuit bias, so this resistance we will not consider. So what you get? Z1 tether impedance, Z equal to Z am writing, that is V1 by I1. V1 by I1. Because rotor current is 0, open circuit, this Z1 is equal to what? R1 square plus, this is XM, this is X1, XM plus square whole root. Okay. So we have measured V1, we have measured I1, so you get Z1, then you know R1, so you get XM plus X1. Then block rotor test, as I have mentioned, the rotor is blocked, stands still, not rotating. So slip is 1. Slip is 1 means current is maximum. So measure I square R losses are the predominant. And in block rotor test, we always start from 0 voltage. In block rotor test, the rotor handle is put and it is not allowed to rotate. We apply small voltage. Small voltage we start from 0, increase it till rated current flows through the ammeter, tetrametry. If the current, so for that you apply only small voltage, you don't have to apply full voltage. So 10-20% of the rated voltage you apply, you will get the rated current. Rated current should not be exceeded. So at 10-20% of the voltage, core loss is negligible. Core loss is proportional to voltage square. So core loss is negligible. So mainly I square R losses are predominant, and you get the equivalent circuit like this. This part is removed. So this way block rotor test you get power factor, the equivalent circuit you get, magnitude of the impedance you get. So this way you determine the parameters. So block rotor test. So there is an example. Achha. So how much time is there? Okay. Let us work out this example to see how the equivalent circuit parameters are determined, so that you also understand. Okay. So data is given. Motor nameplate rating 7.5 HP, 4 pole, 208 volt, 60 hertz. Star connected induction motor. Rated current is 20 ampere. DC test, VDC, IDC is given. No load test data given. Long rotor test. Sketch the perfect equivalent circuit of the motor. Now, machine is star connected. Machine is star connected. DC voltage, VDC, DC test. VDC by IDC, you get the resistance. VDC by IDC is twice the resistance because machine is star connected. So you get one value DC resistance half of that, multiply 1.15, you get R1. Then no load test again, no load you apply the nearly full rated voltage. You apply rated voltage 208 volt, but current drawn is only no load current, which is very small. Because again current is small, I square R losses are also small. So that you get Z1. This is the no load test. This is V1, I1 you get according to this. Z1 you get, and R1 you have already in no load test from this data. V1 is 208 volt, I1 is 8.17, and V1 is how much? 208 by root 3, because machine is star connected and this voltage is line voltage. 208 volt is the line voltage. This V1 is 208 by root 3 phase voltage, and this is I1 is 8.17. So you get Z1. R1 is already determined, so you get XM plus X1. Then you do long rotor test. In long rotor test, V1 is 25. VL line voltage, and I1 is 27.
This is rated.
Sir, in log rotor S equal to 1. Log rotor S equal to 1.
Log S is 1.
So R is minimum.
So you can draw the equivalent circuit for the long rotor test. You have stator voltage, stator current. Here you have magnetizing branch. Magnetizing branch we don't show because we apply only small voltage to get the rated current. So at that voltage this XM is not required. So here you have R2 dash and X2 dash. V1, so this is the equivalent circuit for block rotor test. So what you get? Z1 is V1 by I1. What is V1 is? V1 is 25 by root 3. Per phase voltage V1 is 25 by root 3. I1 is 27.9. So you get Z1. And Z1 is how much? It has two components, R1 plus R2 dash, and another is X1 plus square. You get
Sir,
Z1.
here we are neglecting the core loss component
Totally core loss we are neglecting.
because the voltage is less.
Because voltage is less,
Okay.
less means very small. Because you want only small part of the, you see, 25 volt is where rated voltage is 205. Only 25 volt is required to 10%. Less than even less 10%. So at that core loss is proportional to square of the voltage. Core loss. So if it is 10%, so 10 square 10 means percent means 0.1. 0.1 square is 0.01. 1%. Core loss will be 1%. 1% is definitely negligible. So this is open. Core loss part is open.
Sir, F equal to 15 hertz.
15 hertz. 15 hertz it is not required. Why it is given like that? Not required, but it is not required.
Sir, actually it is locked by belt and pulley. Therefore it is rotating. Still locked, but it is rotating. The machine is rotating. That is
No machine.
very small speed.
No, long rotor test, why it is
Not rotating, not rotating.
not rotating, not rotating. Long rotor means not rotating. It is always locked. So you get Z1 by this expression and you
So
can
if it is totally locked, then how it can deliver the power? The mechanical is there.
in the power it will draw. I square R losses are there. Na? It is not delivering power, it is the power loss. Input power is the loss power.
There is a frequency.
Okay, input power is the loss
Input
power.
power is the loss in the stator copper loss and rotor copper loss.
So input power is input power. Input power that is root 3 V L I L into cos phi. What is cos phi? Cos phi is R1 plus R2 dash, which you already have by Z. So power factor you got, and I1 is there, so you get this component. Or simply cos phi you get input power is given. Input power is given. VLIL is given. So cos phi is Pn by root 3 VLIL. Okay.
So total input power is utilized for the rotor copper loss. That means I square into the
Rotor and stator.
Yes.
Stator and rotor components. No problem.
And frictional loss will be there also.
Frictional loss, there is not rotation. No rotation. Where from where frictional loss?
Only.
Okay. Okay, here only we will stop, and next we will discuss from circle diagram in the next class. You you have done also, I am clapping because you have participated more than 100%. Every 100, that is required. So in your class also it should be something. Now I am talking for you, but when you are talking in your class, it should be like that. Your students should also participate like this. Then only class will be effective.
Interactive should be.
Instruction should be there. Thank you.
ସେ ଏବିର ଗୋଟେ ଭଲ
ଆମର 55 ମିନିଟ୍ସ କ୍ଲାସ୍ ମାନେ ଟାଇମିଂ ଆମେ IMS ପୁଣି କୋଡ୍ କରିବୁ ତା ପୂର୍ବରୁ 5 ମିନିଟ୍ ତ ପିଲା ଅଟୋମେଟିକ୍ 50 ମିନିଟ୍ ପାଇଁ କ୍ଲାସ୍ ନେଇକି ପିଲାକୁ ସାମିଲ
निद लगुच मैडम मैडम काली करियाबा बैटरी को ना मोबाइल लेके दो मैडम हमें रोसे करी खाइबू ना से क्लास करिबू
पिला आजकल हो
बहुत डाकी पाठ पढेबा जबरदस्ती सम्मान छा 50 मिनिट ले करिया मैडम आज पर ती थाउ मोर किन चढ़ो ना मैडम हमें छतवा खाइ के आसु भूख लगी हां केते मन के मैडम सोमवार
विप्रसाद गांधी आधार नहीं से
पानी का सारे डायरेक्ट कर देले का काली साफ कर दिले लागे छोड़ दिए मोरले नाम डिस्ट्रिक्ट नो आसार मु जानि नथि जानले बिटेक ना आदर्श कॉलेज कुंदी आपन को बोलटा कोई
चलती ऐसे लगता नहीं है ଯାଇଥିଲା ପୁଣି ଆସିଲା ଆଉଥରେ
କୋଉଠି ରଖିବା କୋଉଠି ଥିଲା ଜାଣିଛ?
ଏଇଟା ଏଇଠି ଥିଲା
ଏଠି ଥିଲା ମେସିନ୍ଟା
ହୁଁ
ନିଶ୍ଚୟ ଏଠି ଥିଲା।
ଏଇଠି ଥିଲା
କରେଣ୍ଟଟା କୋଉଠି ଆସିଲା ସେପଟେ?
କରେଣ୍ଟ ତ ଅଛି ସେଠି ଗୋଟେ ଖାଲି ଏଇଠି ଲାଗିଛି ଆଉ ଗୋଟେ
ସେପଟେ ନେଇ ଆସିବ ଗୋଟେ ବକ୍ସ ପାଇଁ ରହିବ।
ଏଇଟା ସାଇଡ୍ ହବ କ'ଣ ନେଇଯିବେ କି?
ନାଇଁ ନାଇଁ ଏଇଟା ଆସିଲା ତ